Alright folks, today we're diving into the fascinating journey of how we turn ordinary sand into those sleek, smooth glass plates you see everywhere. You might be surprised at how much goes into transforming raw materials into something as useful and ubiquitous as glass. So, let's get into it. First off, the primary ingredient for making glass is silica sand. This sand contains silicon dioxide, which is crucial for the quality of the final glass product. The journey begins with extracting this silica sand. You can find this type of sand in various locations around the world, and its purity is key. The purer the sand, the better the glass. Once we've got the sand, it's transported to a processing facility where it undergoes several stages of cleaning and preparation. At the facility, the sand is washed to remove impurities like clay, silt, and organic matter. This step is vital because any impurities can cause defects in the final glass product. After washing, the sand is sorted by size to ensure a consistent particle distribution. This is important for the melting process. The cleaning process also removes iron oxides, which can give the glass a green tint. We want our glass to be as clear as possible, so getting rid of these impurities is a must. Next up, we mix the prepared sand with other raw materials. These include soda ash, which is sodium carbonate, limestone, which is calcium carbonate, and various additives depending on what properties we want in the final glass. Soda ash helps reduce the melting temperature of the sand, making the process more energy efficient. Limestone helps stabilize the mixture and improves the chemical durability of the glass. Depending on the desired qualities of the glass, we might add alumina, boron oxide, and various colorants or decolorizing agents. For instance, to produce clear glass, we add decolorizing agents like selenium or cobalt oxide to counteract any coloration caused by iron impurities. Once we've got our mixture of raw materials, it's time to form a batch. This batch is then fed into a furnace where it's heated to incredibly high temperatures, around 1,700 degrees Celsius. At this temperature, the sand and other materials melt and fuse together, forming molten glass. This stage is critical because any impurities or inconsistencies can affect the quality and clarity of the final product. The molten glass must be kept at a uniform temperature to ensure consistent viscosity, which is essential for the forming process. Continuous monitoring and control of the furnace conditions are crucial to maintaining the quality of the molten glass. Now that we've got our homogeneous molten glass, it's ready to be formed into a glass plate. One of the most common methods for producing flat glass is the float glass process, developed in the mid-20th century by Sir Alistair Pilkington. In this process, the molten glass is poured onto a bed of molten tin. The glass spreads out and floats on the tin surface, forming a flat and smooth sheet due to gravity and surface tension. We can control the thickness of the glass by adjusting the speed at which the glass ribbon moves through the float bath. This process results in a perfectly flat and uniform sheet of glass. As the glass ribbon moves along the tin bath, it gradually cools and solidifies. The temperature needs to be carefully controlled to prevent any stresses or imperfections in the glass. After leaving the float bath, the glass ribbon enters an annealing layer. The annealing process involves slowly cooling the glass to relieve internal stresses that could lead to cracking or breaking. The glass passes through a series of temperature-controlled zones in the layer, allowing it to cool gradually and uniformly. This step is crucial to ensure the structural integrity and strength of the glass. Once the glass ribbon has been annealed, it's cut into plates of the desired size. This is typically done using automated cutting machines that score the glass with precision to ensure clean breaks. The edges of the glass plates are often polished or beveled to remove sharp edges and improve the aesthetic and functional qualities of the glass. Edge treatments also help in preventing chips and cracks during handling and installation. After cutting an edge treatment, the glass plates may undergo additional processing depending on their intended use. This can include coating the glass with various substances to enhance properties like scratch resistance, UV protection, or reflective capabilities. For example, glass used in windows may be coated with low emissivity coatings to improve energy efficiency. These coatings reduce heat transfer through the glass, keeping buildings cooler in summer and warmer in winter. Safety glass, like that used in automobiles and buildings, may undergo processes like tempering or laminating to increase its strength and shatter resistance. Tempering involves reheating the glass to around 600 degrees Celsius and then rapidly cooling it with air jets. This process creates compressive stresses on the surface of the glass and tensile stresses in the interior, making the glass much stronger than untreated glass. Tempered glass is also safer because it breaks into small, blunt pieces rather than sharp shards, reducing the risk of injury. Laminated glass is made by sandwiching a layer of polyvinyl butyryl or another tough plastic between two layers of glass. This process not only strengthens the glass, but also holds the pieces together if it breaks, reducing the risk of injury. Laminated glass is commonly used in windshields and other applications where safety is a primary concern. In addition to safety, laminated glass also provides benefits like sound insulation and UV filtration. Quality control is an essential part of the glass-making process. Throughout the production stages, the glass is subjected to rigorous inspections and tests to ensure it meets the required standards. This includes checking for visual defects like bubbles, inclusions, and scratches, as well as measuring optical properties like clarity and light transmission. Mechanical properties such as strength and durability are also tested to ensure the glass can withstand the conditions it will be exposed to in its final application. Advanced techniques like laser scanning and automated inspection systems are often used to detect and measure defects with high precision. The entire process from raw sand to finished glass plate is a blend of ancient techniques and modern technology. It requires precise control of temperature, chemistry, and mechanical processes to produce high-quality glass that meets the demands of various industries. The ability to transform a simple material like sand into a versatile and essential product like glass is a testament to human ingenuity and technological advancement. Over the centuries, improvements in the understanding of materials science and manufacturing processes have enabled the production of glass that is stronger, clearer, and more durable than ever before. In summary, making a glass plate from sand involves several critical stages. The process starts with extracting and preparing silica sand to ensure purity and consistency. This sand is then mixed with other raw materials like soda ash and limestone. The mixture is melted at high temperatures to form homogeneous molten glass. This molten glass is then formed into a flat sheet using the float glass process. Next, the glass undergoes annealing to relieve internal stresses and ensure uniform cooling. The glass ribbon is then cut into plates of the desired size, and the edges are treated. Additional coatings or treatments may be applied to enhance specific properties. Throughout the process, quality control tests are conducted to ensure the glass meets the required standards. Each step in the process is meticulously managed to produce high-quality glass that is essential for countless applications in everyday life, from windows and mirrors to electronic screens and laboratory equipment. The journey from sand to glass plate is a remarkable example of the transformative power of science and industry. This intricate process highlights how raw materials can be turned into sophisticated products that play a crucial role in modern technology and infrastructure.